Donc, thank you very much to the review. My name is Jean-Louis Consalvi from Aix-Marseille University, and it is a big pleasure for me to serve as a chair. The title of the presentation is on the importance of heat-release rate in numerical simulation of fires in mechanically ventilated tight enclosures by Bart Merci, Ginuli, and Georgios Marakos. The speaker is the Professor Bart Merci from Ghent University. Professor Merci is a well-recognized professor in the field of fire research and also turbulent combustion, and it is to you.
Merci, Jean-Louis. Thanks for being here. Thanks for coming to listen to me. I'm obviously honored and humbled and to have been invited to give a topical review in the field of fire research, and so I'm very grateful to whoever was involved in this decision-making process. Now what I will present to you, and I'll try to make it a bit more readable, is a talk on the very important quantity that's called the heat release rate, and that's of course a very broad topic, so we needed to go a bit more specific in terms of trying to limit the review. So we limited it down to fires in enclosures, and that is still too broad. So we went then to numerical simulations, and that is still a very broad topic. So in the end, we decided to focus on airtight, mechanically ventilated enclosures. Now, much of what I will present to you has been developed based on insights that we gained from CFD simulations that were done by Dr. Georgios Marakos from my team. So that's why he is also co-authoring this paper. And as I will show some results on these mechanically ventilated airtight enclosures, most of these results stem from the PhD work of Juanyi Li, which is why he's also a co-author of this paper. So some of the things that I will say are opinions, and I'll try to be explicit about that. Some of the things that I will say are applicable to any compartment, and some will be specific to these airtight enclosures. And I'll start off with the energy equation to highlight the importance of the heat release rate. I'll say a few words about scaling, because this is something that is very common to do in the context of experiments. But then I'll move on and take you along on a small journey in CFD simulations, focusing on modeling and saying a few words on how to deal with extinction phenomena and possible reignition. And I'll wrap up with a phenomenon that is very specific for these airtight enclosures to some extent, but not really, and that's the low frequency oscillations that are sometimes observed. And I'll try to end with some conclusions and an outlook. So the context why we are interested in these airtight enclosures is you see this as a modern trend in buildings in terms of reduction of energy consumption. Houses are better and better insulated and made more and more airtight. There's also applications in industry, for example, the nuclear industry, where you have to avoid the spreading of radioactive material in case of an incident. But also if you have windy regions on this planet with high-rise buildings, then these are also airtight. And this can be problematic in the context of a fire, because if you have a fire, then hot combustion products are released. These hot combustion products have the tendency of occupying more volume than products or gases at ambient temperature. So in combination with a low leakage area, this leads to substantial rises in pressure, which in its turn can hinder evacuation of people from a building, because it's very difficult to open doors. If you have a pressure higher than 200 Pascal, then even the best trained person here in this audience would not be able to open a door. But it can also compromise structural integrity and can lead to a loss of confinement, and this can be in a dynamic way and due to the fire dynamics, and thus this safety issue can be a problem. So let's move on to the energy equation, which is well known, but it's shown here in the context of these airtight compartments. So what you have here is a few important quantities. So one that you see moving around is the fire, and that fire has a certain heat release rate, which is the topic of this talk. So this brings energy into the compartment per unit time. At the same time, also gases are released, so that's a mass flow rate of gases entering this compartment. But you also have heat losses through the walls, so that would be a sink term in the energy equation. And you have, you see a pointer moving around, which is pre-recorded, so it's not so easy for me to follow my own pointer now, so don't be distracted. You also have some flow rates entering and perhaps extracting also gases into this compartment. So basically what you have, if you look at the red graph, you have here an evolution of the heat release rate as function of time. And if you look at the resulting pressure, that's the blue curve, you see that you first have a pressure rise as function of time as the heat release rate increases. But then as the heat release rate is constant over time, there is a relaxation of the pressure back to its initial value. And when you have a reduction of the heat release rate in time, you have a drop in pressure as function of time. Now that cannot be explained directly from the energy equation as you see here at the bottom of the slide, because there you would expect a continued increase in pressure as function of time as long as the heat release rate is higher than the losses through the walls. I should inform you that the heat flow through the ventilation system is a relatively small term, and you can easily imagine, hopefully, and that if you have a heat release rate inside the gas phase, that it takes a while until this heat is lost through the walls. So in principle, this is a bit strange at first sight, but it's not, and we tried to explain that because these flow rates that you see here admitting and extracting gases, they would also depend on the pressure inside the enclosure through the characteristics of the fans. So one way to look at this issue is to say, well, this is an overall equation for pressure as function of time, so we don't really need to have much detailed information on the flow field and to try to get this pressure evolution. All we need is an estimate of the heat release rate, the heat losses, and that's it. So you can indeed go for analytical solutions and zone model type of approaches where you would have a single zone or maybe two zones inside the compartment, but not more than that. I should say that the heat losses are not so easy to quantify, and they are important to quantify, but that's not the focus of the present talk. And there will be this complex dynamic interaction with the mechanical ventilation system. Now, if you want to be really predictive and including a prediction of the heat release rate, then it will be important to have more detail on the flow field, because you need to know what's happening in the region where the fuel is released. Again, this is a small disclaimer, and there is, these slides are changing automatically apparently, and there is a small disclaimer here. It's very important if you have a liquid fuel or a solid fuel to model the evaporation of the liquid fuel or to model the pyrolysis of the solid fuel. These are very interesting and important topics on themselves, but I'm not going to address those. So I'm only going to focus on gas phase phenomena, and I'm going to use here results that we obtained with gaseous fuel. And even that is complex enough, as I will try to explain. So when I say we, I actually do not mean only at Ghent University. We had a very good collaboration with IRSN in France, where former PhD student John Lee spent a few months to do some experiments in what is called the NICS setup. The details you can find in the paper, but it's a rectangular box. You see the size here on the slide. And what is specific in this study is that he used gaseous propane fuel that you see there in the red square on the sketch. And this was fully instrumented, so with thermocouple trees, with pressure measurements, even with some measurements of species. So we had pretty good control over what was happening, because we could monitor and we could actually control the gaseous fuel flow rate into the compartment. The blue line is the supply duct for air, and the red arrow that you see there was the extraction of the hot gases. These give you some impression of some pictures during the tests. These were provided by Dr. Hugues Prétrel from IRSN. So the top left is the ignition of the pilot flame, and then the second one is the real ignition of the gas fuel, and then you have some steady burning phase where we have a constant heat release rate as function of time, but obviously things are turbulent, so the flames are fluctuating, and at some point we chose to extinguish the flame in a controlled way. And the idea was to vary certain parameters and to try to understand what is the resulting pressure evolution. So what you see here as one of these results is we start off with a zero fuel mass flow rate, and we switch on the ventilation system. So you start with some under pressure, which is typical in the context of nuclear industry, for example, so that you do not have gases escaping from the enclosure. And once we ignite the gases and we start to feed the compartment with fuel, which is the red dotted line, you see we have a sudden increase in pressure as function of time, and as long as we keep increasing the heat release rate, also the pressure keeps increasing over time. And then we keep the heat release rate steady state, and you indeed see this relaxation of pressure back to somewhere close to the initial value until we choose to reduce the heat release rate as function of time, and then we have a significant underpressure inside the enclosure. And then if you allow the system to cool down and you keep the ventilation system switched on, your pressure goes back to the initial value. But as I said, I mean, this cannot readily be explained from this equation because you would expect a pressure rise as function of time as long as the heat release rate is dominant. Now, the interaction is much more complex, and I will not spend too much time on this, but you can go and look at this in terms of an electrical analogy, where the enclosure works as a capacitance in the circuit, and then you have different sources. One would be the fire, the other two would be the ventilation fans, and you would have flow resistances through the duct systems, and that would lead to some complex interaction. You can study the whole thing, or you can study the ventilation only, or you can study the fire only. And then in the end, if you do that and you do some time scale analysis, you do indeed find this theoretical result that in certain circumstances, it's the pressure rise rather than the pressure derivative as function of time that evolves directly with the difference between the heat release rate and the losses through the walls. So this was very good. I'm sure you can not easily see the lines in the left plot here, but there we tried to visualize the different individual terms in the energy balance, and then you see indeed that the heat release rate and the heat losses are the dominant ones. So this was very reassuring, but it also shows the importance of the heat release rate, which is the topic of this talk. This gives you an overview of what we varied. So we varied the speed with which we increased the heat release rate. We varied the duration. We varied the maximum heat release rate. Many parameters that we did. So quite extensive experimental campaign, and that we could then use to check and validate our numerical results. Now, before getting into the CFD part, a few words on scaling. So in fires, the scaling laws are actually well known. So what is done is so-called Froude scaling, where you use the Froude number to keep constant. If you do that, then you can find that the heat release rate has to scale with the length scale to the power 2.5. So nothing very special there. But it does become much less straightforward if you have to combine it with mechanical ventilation, because then you have different factors coming in. You also want to keep an eye on the global equivalence ratio, because if you start changing flow rates and you start changing the global equivalence ratio, you can start changing the regime between well-ventilated and under-ventilated conditions. And we are also looking here at transient phenomena, so we have to keep an eye on time, which scales with the square root of the length scale. On top of that, I told you already that the heat losses are important, and these are not so easy to scale because the material behaves as thermally thick. So if you use the same material, then the relative contribution of heat losses changes at full scale versus at small scale. So what you see here in this plot is the relative contribution of the heat losses by conduction into the wall at reduced scale, which is the blue curve, compared to the full scale, which is the red curve. So as you can see, relatively speaking, you have more heat losses at reduced scale, so you would expect for a well-scaled heat release rate as function of time, a lower pressure rise, because the heat losses were a sink term in this pressure equation. And this is indeed confirmed here, so this gives you some flavor of what you could do with CFD more easily than in experiments. So what you see here are three lines. The bottom line, it's in blue, are results at reduced scale. So you have pressure evolution as function of time. This is the lowest value here because the heat release rate is scaled with length scale to the power 2.5. So if you reduce the heat release rate, you have a reduced pressure rise. The dotted curve, the dotted line that you see here are not experimental data. It's just the blue line multiplied by a factor of 4. Now, why by a factor of 4? That's because we did that, we found that through the scaling laws, how pressure should scale. So that's what you would expect from just scaling experimental results from small scale to full scale. Now these give an underestimation of the pressure rise. You see the red curve are CFD results directly at full scale. So indeed, as expected from the previous slide, as you have relatively speaking less heat losses at full scale, you go to higher pressure rises at full scale. So this is just a warning in terms of experiments. If you go to reduced scale for these types of experiments, you have to be a bit careful when scaling them. This is in terms of the maximum pressure, but there's also an issue with the transient phenomena. So as I said before, time scales with the square root of the length scale, but as these are pretty fast pressure changes as function of time, it becomes less straightforward to do the proper scaling. I have to go back a few slides now, and so apology for that, but this theoretical result, if you look carefully, it's not exactly equal to, it's approximately equal to. And if you do the analysis on the original energy equation, which you see over here, then you see that some of these terms scale differently with length scale if you look at it as function of time. And that's something that we also illustrated here. So what you see here again is not experimental results, but just differences between CFD simulations. And you see that the transient at full scale is different from the one at reduced scale. Again, something I think worth exploring a bit more in the future, but that's an opinion. So let's have a look at CFD simulations. I think if you want to see the state of the art of CFD modeling today in the fire safety science community, it's probably a good idea to check the website of the MACFP workshop series. MACFP, for those who are less familiar with this, is Measurements and Computations of Fire Phenomena. It's a very nice GitHub-based website where you find a lot of simulation results, experimental data, and you get a feeling, a flavor of what's happening today in the CFD simulations of fire. And the common approach that is used for turbulence is the large eddy simulations approach. DNS is not affordable, and unsteadiness is too important for RANs to be popular in the community of fire safety science. So turbulence is addressed with the large eddy simulations. Now, at Ghent University, we believe that the dynamic approach to model subgrid scale quantities has some potential. And you can do that for the turbulence, you can do that for the combustion, you can even, to some extent, do that for length scale determination in radiation models. So we believe this is worthwhile investigating. We'll see if this is true or not, but so far, Georgios Marakos has done quite a number of simulations with reasonable success. Now, combustion, here at the Combustion Symposium, this may seem quite old-fashioned, but the eddy dissipation model or eddy dissipation concept with infinitely fast chemistry is actually the most popular tool today. And that is because the length scales and the time scales in fires are significantly different from the ones that you would have in flames that we see here most often here at the symposium. So this is the most common approach, but mixture fraction-based models are used as well. Again, I just remind you of the fact that I'm not talking about evaporation. I'm not talking about pyrolysis. These are key aspects in most fire simulations, but do not have the time to talk about that here. So just want to give you a little bit of feeling of what are key elements, key differences between, on the one hand, EDM, EDC, and on the other hand, mixture fraction-based models. Now, the EDM, EDC models, they are applied directly on a CFD mesh. And this gives you a very strong advantage in that the heat release rate, which is then typically calculated as the product of the reaction rate and the heat of combustion of the fuel, is directly present as a source term in the CFD equations at the CFD mesh. So that means that if you know how much fuel you are injecting into the domain, and if the combustion is complete, then you automatically get the correct total heat release rate. And that's very useful, because then if you have a reduced heat release rate, you can use that as a measure to quantify the completeness of the combustion inside the compartment. Be it airtight or not, this is just a general statement. But an obvious major disadvantage is that the chemical kinetics are ignored. So in that sense, you may want to look at mixture fraction-based models, where you can have much more information in terms of chemistry and temperatures at a relatively low price. But what we discovered as a major disadvantage for these models in the context of fires at least, is that the heat release rate is now primarily determined in mixture fraction space. And you somehow have to bring that information back onto the CFD mesh. And that's less straightforward than we thought it would have been. Now, what is specific about fire in contrast to the jet flames that we often see here is that we have a relatively low, very low, I should say, scalar dissipation rate, or conditional scalar dissipation rate, because everything is driven by buoyancy, and we have very low velocities in the orders of a few meters per second, and that's the order of magnitude. This, in turn, leads to very slow mixing rates of the fuel and oxidizer compared to jet flames, again, leading to long response times of flames. It also leads to low stretch rates in the flames, and so the flames become physically thicker and also optically thicker, which has issues in the context of radiation, which is always very important mechanism of heat transfer in the context of fire. So if you think in the framework of the unsteady laminar flamelet approach, then these unsteady effects have been mentioned to be important for radiation by Heinz Pitsch almost 20 years ago. So this is well known, but it's something that is still an issue in the context of fire. Now, when I said that it's not so straightforward to find the correct heat release rate on the CFD mesh, we first thought that we did something wrong at Ghent University, until recently we saw some work at the University of Poitiers in collaboration with Arnaud Trouvé in Maryland, where they report this, that in the context of laminar flamelet modeling, that it's not straightforward to recover the heat release rate. And they suggest an approach that I think, it's an opinion, but I think is very interesting to explore, is not to look at the local scalar dissipation rate, but to also take into account some history effects. And these history effects are important because of the slow response times of the flames to these stretching rates. So I think this is something worthwhile exploring. Also in the context of CMC, we also found that it's not straightforward to find a good value for the scalar dissipation rate. And on top of that, that's work by Boris Kroljevic. He also figured out that when radiation is important, and it's always important in fire flames, or almost always important in fire flames, that it's not good enough to have high accuracy around stoichiometry. You really need to have good accuracy over the entire mixture fraction space range. So these are a few closing notes here on mixture fraction-based combustion models. Now, I would like to say a few words about extinction and reignition, because that's also very important to know in the context of compartment fire dynamics. And now, if you use this EDM-EDC approach with infinitely fast chemistry, there is no way to do this from a chemical point of view. So you need to find another way around this, and then it's interesting to check what kind of extinction phenomena can you expect. And again, there is a fundamental difference with extinction at high strain rates, at high scalar dissipation rates, on the one hand in jet flames, and extinction phenomena in fire flames on the other hand. Because again, strain rates are low, scalar dissipation rates are low. So this aerodynamic quenching, which is very common in high velocity flames, is not found in fires. Rather, the main quenching mechanism in fire flames is actually a thermal mechanism, where heat losses from the flames by radiation, for example, become so large that the temperature becomes too low for the chemistry to continue, and that's how you can get to quenching. Another way of quenching is through dilution. If you have mixing of oxygen with combustion products, that then again, maybe there is too little oxygen left to have a significant rise in enthalpy, a significant rise in temperature, and again, the combustion stops. All of this can be approached through the Dampkühler number. So that would be the unifying approach. But nevertheless, in engineering type of calculations, it's a bit easier to work directly with the temperatures that you find in CFD cells. And this is an approach that is followed in the FDS code today, where you work with a so-called critical flame temperature, and you check whether the conditions inside a CFD cell are such that it's possible to raise the temperature upon complete combustion beyond a certain critical flame temperature. So this ignores the possibility of vitiation to some extent, and certainly of aerodynamic quenching, but it works pretty well. And actually, I should be a bit careful here. Vitiation is taken into account to some extent, because also the oxygen concentration is taken into account. There are other approaches. So for example, Professor Snegirev, he introduced this idea of working with a perfectly stirred reactor at subgrid scale level. So the fine structures concept is used. And then from that perspective, he also arrives at a critical Dampkühler number with the possible advantages that you can now easily, automatically, well, not easily, but automatically work with vitiated conditions, and that there is no need also to distinguish between premixed or non-premixed flames. Now, extinction is one thing. Spurious reignition, so unrealistic ignition, where temperatures would be too low to really have ignition, but where the modeling forces ignition, that is a sometimes even more important issue, because that could give you flames in CFD simulations where they are completely unrealistic, where they would not be in reality. Also here, you could again follow an engineering approach and say that you can only have ignition beyond a certain critical temperature. So that's one approach. A very interesting, I think, recent theoretical framework was introduced by Dr. Sergei Derofeev. If you want to have more details, feel free to talk to Sergei, where he worked with the concept of mixed eddies. And that would give you some unifying approach for extinction and reignition. So just as a closing note here, I am saying that thermal quenching is very important in fire. That is due to radiation mainly, so that obviously implies that radiation modeling and soot modeling are very important in the context of fire, and still a lot of work to be done there. Okay, that's what I wanted to say about the modeling. You can look at the paper for more details. So just some final section here is to look at some low frequency oscillation phenomenon, which is something that was observed in the context of the PRISM project, which was also then organized by IRSN in France, where they saw this low frequency phenomenon, low frequency meaning oscillations in the order of 0.023 millihertz, so very slow phenomena, and they observed that with liquid fuels. And they also saw that they only had these low frequency oscillations when the temperature inside the compartment was sufficiently high and the oxygen concentration was sufficiently low, actually not too far from the extinction limit. So the assumption is that this should be linked to the global equivalence ratio. And one of the ideas is that if you have this combined dynamics between fire dynamics and oxygen supply, that in some conditions, if you have a strong fire, you would have less oxygen supply due to this pressure rise inside. The fire becomes weaker, so then you have more oxygen supply through to this dynamic coupling, and the fire becomes stronger again. And this could then be linked also to displacement of flames away from the liquid fuel. So the common thinking is that this was directly linked to the evaporation of the liquid fuel in the compartment. I'm mentioning all of this in the context of the PRISM project, but these low-frequency oscillations have also been observed a long time ago already in Japan and in US with natural ventilation. So it's not linked per se to this mechanical ventilation aspect. So we wanted to challenge these hypotheses, and so in these next studies where we now have gaseous fuel, we wanted to see if we can also have these low-frequency oscillations, because if we do, it's not only linked to evaporation of liquid fuel, because we don't need to vaporize the fuel anymore. On top of that, we also see in the literature increased evidence that this global equivalence ratio, while it is obviously important to characterize the combustion regime, is definitely not sufficient to characterize everything, because results have been reported where there is a big difference depending on the position of the inflow of air. If you supply your air close to the burner, it's completely different from supplying the air close to the ceiling, even if you have the same global equivalence ratio. So that shows that it's important to have knowledge on the details of the flow field, which brings upon the importance of CFD. So for the sake of time, I'm going a bit quicker. I just immediately go to this result, which is a result again by Joigny, where you can clearly see in the top left figure, this is the heat release rate that was imposed, that the pressure rises as it commonly does, and then you start to see these low frequency oscillations. So with this, we illustrated that it's not only linked to evaporation of liquid fuel, that you also see it in gas fuel. The fast Fourier transform analysis shows a very distinct peak, so it's very easy to characterize, and interestingly, it's the same frequency as tests that were done by Maxime Mans in Marseille before with liquid fuel. So the frequency is the same, even though the fuel was completely different. The other graphs are the supply flow rates and the global equivalence ratio. And the global equivalence ratio does not go beyond 0.25. So this is far away from 1, far away from underventilated conditions. So this brings me to the argument that there is a very strong need, I think, that's an opinion, and to look more into detailed interaction between flows and flames. And this again is a significant difference from a well-controlled jet flame, where you have well-controlled flow fields, versus a flow field with a fire, where the fire itself changes the flow field. So you have very complex interaction between flows coming horizontally, coming vertically in the flames, stretching them, moving them around, and all of these at low scalar dissipation rates. So I would argue that it's very important to focus strongly on more on this interaction between flow field phenomena and combustion phenomena in the context of fire. These are just a few snapshots to further illustrate the point. So this was at the start of the fire, and the right-hand side is the vertical plane through the fire. The left-hand side is the vertical plane through the admission duct. So you see a strong vertical flow on the fire, and then when the fire gets weaker, you have stronger inflow through the admission duct. And then as the fire extinguishes, you have an even stronger inflow at the admission duct during this under pressure period. So this brings me to the conclusions and some outlooks. So the context was airtight enclosures where you have a fire-induced pressure rise. Going into the energy equation, I tried to explain that it's important to know the heat release rate and the heat losses per unit time. That scaling is never going to be perfectly possible, and particularly the heat losses and fast transient phenomena are hard to capture. In the context of turbulent combustion modeling, I tried to say a few words on the importance of extinction and reignition. That I believe, that's an opinion, that the mixture fraction-based models are still worth exploring, but we have to look into this low conditional scalar dissipation rate phenomenon and how to get the correctly integrated heat release rate in the CFD mesh. Thermal quenching is key, so radiation soot, very important, and at Ghent University we believe that the dynamic approach might be appealing. And then finally, these low frequency oscillations, the global equivalence ratio is important, but not enough to characterize what's going on. It has been observed now also with gaseous fuel, and the detailed knowledge of the flow field is key. So there is a lot of potential for CFD, I think also outside of what I said here. So if you look at traveling fires, which I prefer to call moving fires, large open plan fires, configurations where wind is important, all of these things, I think CFD has a lot of potential to try and build some more insight. And I'd like to conclude by acknowledging all the researchers who contributed over the past few years to this research, and of course all the funding agencies. Some colleagues have reviewed the paper before it was submitted here, so also thank you to them, and obviously thanks to Yorgos and Joigny and to you for listening to me. Thank you.
We have time for question, so present yourself when you ask the question, please. The microphone is there.
I think you have to move to the microphone, Jennifer, that's standing there.
Yeah.
Or the microphone is coming to you.
Is this working?
Yes.
Yeah, Heinz Pitsch from Aachen. I mean, you mentioned the fact that it is difficult to match the heat release, even though everything should be conserved. And I just want to make a comment. We have addressed this issue, and in fact, the next talk, the very next talk in the turbulent combustion session is going to address this topic. Yeah.
Thank you, Heinz.
Thank you for the excellent talk, Bart. You mentioned several times that you would prefer a direct approach for radiation and soot. Can you elaborate on that?
Oh, I think actually probably Jean-Louis can elaborate better than me on that. So there is many models on the market. Well, one problem in fires is that we often do not know the fuel in advance, so that makes it quite difficult to go to very detailed spectral-based models if you don't know the composition of the gases. Soot is more gray, as we know, but then developing good soot models to have the good soot concentration is also often problematic. So what I think is that we need to find some balance there between accuracy, complexity, and robustness. And I don't have a clear answer for you right here, right now. I just think that a lot of work still needs to be done to get the first order quantities even correct. That's the best I can say right here, right now. As I said, I mean, Jean-Louis is more an expert than I am in this field, and probably you will agree that a lot is going on in that field. Yeah.
So no more question. We can thank again the speaker.